let's discuss the factors which affect electron affinity. The first and foremost factor is nuclear charge or effective nuclear charge. Let's consider this example. If this is the nucleus, this is an example for a fluorine atom. If the nuclear charge is more, it will attract the core electron as well as the valence electrons towards itself. So the 1s is the core electron in the case of fluorine, 1s2, right? And the second sublevel 2s2, 2p5, that is the valence shell. So if the atomic number is more, which means Z is more, the nucleus will attract the core electron as well as the valence electrons towards itself, right? In the case of S subshell, due to its spherical symmetrical shape, it is more penetrating towards the nucleus field. So this increased nuclear charge also attract the incoming electrons towards itself, right? So this will ease the approach of or the acceptance of the electron, the incoming electron. So if the effective nuclear charge increases, the acceptance of a new electron will be more easier. As a result, electron affinity also get increased. So this electron will occupy a position because of very high nuclear charge. The second one is, that's the reason why when across a period effective nuclear charge increases, electron affinity also increases across the period. Whereas in the case of atomic radii, the second factor, the atomic radii, when down a group, when this is a nucleus, okay, if here electron is there, here also electrons are there, 8 electrons are there, and here also electrons are there. When an incoming electron is come, due to the presence of the core electron, okay, the core electron is there, and the size of atom, if the number of energy levels are added onto the atom, going down a group, the number of energy levels is increases. So the atom will become bigger in size. As a result of that, the effective nuclear charge of this electron, the incoming electron does not feel much attraction from the nucleus. Two factors there. One is due to the increased size, atomic radii. The second is the shielding effect. What is the shielding effect? I will discuss the shielding effect. The shielding effect, that is the inner core electron, shield the outermost shell from the attraction of the nucleus. As a result, the nuclear force of attraction, the nuclear charge, cannot be passed on to the incoming electron. So, effective nuclear charge decreases when atomic size increases, electron affinity also get decreased. So when atomic radii increases, electron affinity decreases. So electron affinity down a group decreases. So we can say that nuclear charge is proportional to electron affinity, whereas atomic radii is inversely proportional to electron affinity. Third factor is the electronic configuration of element. We have already discussed it in the periodic trends that a fully filled electronic configuration and a half-filled electronic configuration resulted in approximately zero electron affinity. We have already learned in the case of noble gases. In the noble gases, S2P6, this is the electronic configuration, right? That's the reason why neon, argon, krypton, xenon, and radon, almost all noble gases having zero electron affinity. And noble gases showing zero electron. And group 2 metals, that is beryllium, magnesium, calcium, etc. So this is having an S2, right? 2s2, 3s2, 4s2. That is the outermost subshell. S subshell is completely filled. What about zinc and mercury? In the case of zinc, 3d10 4s2. In the case of mercury also, a completely filled d orbital and outermost s orbital. So completely filled electronic elements having completely filled electronic configuration showing a very less electron affinity. This is because a completely filled is already they have completed their octet, so they does not have a tendency to accept one more electron to form an anion. That is obvious. So noble gases, group 2 metals, zinc, mercury, cadmium, etc. are showing zero affinity. Similarly, half filled, like fully filled, nitrogen is having 2s2 px1, py1, pz1. This is the outermost electronic configuration of nitrogen. See, in the outermost electronic configuration, there is a second period 1s2, 2s2, and 2p3, right? The p subshell of nitrogen and s subshell is fully filled, p subshell is half filled. So, and in the case of manganese also, which is 3d5 and 4s2. Okay, in the case of manganese. So, a half filled D subshell and fully filled S subshell. So we can see that a half filled subshell also showing a nil tendency to accept an electron to form an anion. Okay, so these are the two factors. Electronic configuration of an element is important in determining electron affinity. The fourth factor is electron-electron repulsion, which is very important in determining the electron affinity of an element in periodic table. So the trend of electron repulsion is not general, but in every case, electron-electron repulsion is exist. According to Coulomb's law of force of attraction, when two charges are distanced apart by the distance r, the force of attraction between these charges is proportional to the magnitude q1 and q2 of charges divided by r square. So this is equal to k q1 q2 divided by r square. This r is the atomic radius in the case of nucleus. If this is the electron, right? This is r. The two charges. Nucleus is having a q1 is the nuclear charge, and E is the q2 is the electron, the charge of electron. So similarly, we can say that F is the force of attraction between the nucleus and the electron. Q1 and Q2 are the charges of nucleus and electron. R is the atomic radius. Okay. When these two charges are different, here it is positive and negative. If it is the distance between the electron and the incoming electron, what will going to happen? If the light charges are come closer, the negative and negative, two electrons, right? When two electrons have come closer, what will going to happen according to Coulomb's law? It will repel apart, right? It will repel apart. So in order to avoid such a repulsion, the electron will occupy in a position as far away as possible in order to avoid such repulsion, right? So in that case, the incoming electron does not feel much attraction from the nucleus, or in other ways, it is away from the proximity of the nucleus. In order to avoid such repulsion, the electron-electron repulsion, the incoming electron will occupy in a position which is not in the proximity of nucleus. In that cases, the effective nuclear charge decreases. So we can say that electron-electron repulsion is existing in almost every cases when an incoming electron approaches to an atom. The atom is already having an electron in the valence shell, or the electron cloud will repel the incoming electron, the approach of the incoming electron. As a result of that, the incoming electron experience such a repulsion. It will not have a tendency to occupy the position in the valence shell, or it will always overcome the effective nuclear charge on the incoming electron. So in order to avoid such repulsion, the incoming electron will occupy in a position as far away as possible. As a result of that, the effective nuclear charge on the incoming electron also decreases, and finally electron affinity also decreases, right? So this is the reason behind fluorine is having very less electronegative electron affinity than chlorine. The fluorine, the electron affinity of fluorine is 332 and electron affinity of Cl is 348. Okay, this is the reason why fluorine is having very less electron affinity than chlorine. We will discuss about this in detail. So electron repulsion is very common, and due to electron repulsion, the incoming electron does not feel much attraction from the effective nuclear charge, or we can say that if electron repulsion is more, the effective nuclear charge is very less. As a result, electron affinity will be get more. And when the size of the atom is more, the incoming electron has enough space to occupy. So in that case, the magnitude of electron repulsion is less. Okay. The fifth factor is nothing but it is the screening effect or shielding effect. We have already learned about this screening and shielding effect in ionization energy classes. So here also the same concept. It is the effect where the inner core electrons will shield the valence electrons from the field of attraction of nucleus. That means here this is the valence electron, right? This is valence electron, and this is the nucleus, and this is the core electron. These are called core shell, right? This is the core shell. Okay, so we can say that this is a 1s and this is 2s and 2p. Okay, let's take it as an example. So these two are the valence electron. So the nuclear charge will attract the valence electron towards itself. It has the attraction to all the electrons. So it will attract the core electron as well as the valence electron also. When the nuclear charge increases, it will attract more. So when the shielding effect is, the core electron will act like a shield or like an umbrella or like a screen. It will act like an umbrella and shield the valence electron from the force of attraction of nucleus. As a result of that, this nuclear charge on this valence electron will decreases. When shielding effect is more, effective nuclear charge will become less. And as a result of that, it will not, the effective nuclear charge less means the incoming electron does not feel much attraction from the nucleus, so electron affinity also decreases. So moving from across a period, the shielding effect shielding effect is very less because of the effective nuclear charge is more. The incoming electron is added onto the same energy level, right? The same energy level. So shielding effect is also poor. So electron affinity increases. But down a group, when moving down a group, atomic radii increases, right? When atomic radii increases, the number of core electrons also added. The number of core electrons will be increases. Why? Because the energy level, the number of shells also added. Number of shells added means number of core electrons added, and as a result of that, screening effect increases, decreases, and electron affinity decreases down the group. Right? Electron affinity decreases down the group. Now we will look into which subshell is having more screening effect. Okay. So we have already discussed that in the ionization energy class, where I have already discussed the size of the subshell is having very crucial importance, crucial role in determining the screening effect. So if the symmetry is more, then the screening effect is also more. In the case of S subshell, the screening effect is very high because it is having a spherical subshell and the S electron, the proximity of X electron in the nucleus is more. Okay, the probability of according to quantum mechanical concept, the probability of finding an electron in the S subshell is more because of its spherical shape. So it will screen the effective nuclear charge. It will screen the effective nuclear charge in a high order. So see, this is the case of this is the nucleus, and this is the case of S subshell, and this is the P subshell. If an S electron, if S subshell is the core one, if S subshell is the core, it means, and this is the P subshell is the valence. If it is electron is there, the S electrons will have the probability of finding S electron is around the sphere, right? According to quantum mechanical concept. So this S subshell will screen effectively the nuclear charge. It will screen effectively the nuclear charge and protect the valence subshell. Protect, and it will screen the effective nuclear charge and protect the P subshell. Right? So this is the reason why S subshell is having more screening effect than P and then greater than D and then greater than F. Do you know the F subshell is having very lowest screening effect because of its unexpectedly its structure is not yet exactly determined. D subshell is having a flower-like double shape. P subshell is having a dumbbell shape. So both is not symmetrical, or the effective nuclear charge it cannot screen the outer shell like that of S because S is spherical, right? So this is the order of screening effect. S subshell is greater in screening effect than P, than D and F. Okay. The sixth factor of an electron affinity is called penetration effect. That's I am going to discuss here. The penetration effect of an electron or penetration power. Okay. So it is defined. It is defined as it is the ability of an electron in a sublevel. It is an ability of an electron in the sublevel to move closer to the nucleus. So here, this is the pictorial representation. I have a pictorially represented the three sublevels. The S sublevel, that is the spherical in shape. The P sublevel, that is the dumbbell in shape, and the D sublevel, that is a flower-like double shape, right? Nucleus is in the center. It is the ability of an electron to move closer to the nucleus. So, how closer to the nucleus? More penetration effect is. Penetration means to move closer to the field of attraction of the nucleus, right? So, here, according to quantum mechanical concept, the S subshell, S subshell is having a spherical shape, and the probability of finding an electron is more in the case of S sublevel. So, S sublevel is more penetrating to the nucleus. This is the reason why the penetration effect order is S greater than P greater than D greater than F. So the S subshell is having more penetration effect than P sublevel. This is very evident from the pictorial representation because of the symmetrical spherical shape. The electrons of S electrons having more ability to move closer to the nucleus. So as a result of that, the S electron will experiences more penetration effect. If in the case of when we consider the penetration effect, when we are applying the penetration effect onto the electron affinity, if this is the nucleus and this is the S subshell and an incoming electron, when an incoming electron is added onto a shell which is having more penetration effect, if this shell is having more penetration effect, please remember, when an incoming electron is added onto a shell which is having more penetration effect, what will going to happen? This electron will attract more towards the nucleus. So the effective nuclear charge increases. More penetration effect means the ability to move closer to the nucleus is also higher. So Z effective increases. As a result of that, electron affinity increases. Right? Similarly, if the incoming electron is added onto an energy level which is having lowest penetration rate, what will going to happen? If the size of the atom is more, if the atomic radius is more, see, if this is the nucleus, if the incoming electron, if the electron is added onto an H subshell, H subshell is having very low penetration effect, right? If it is added onto an H subshell, the effective nuclear charge, the penetration power is very less, which means the electron is not having such an ability to move closer to the nucleus. As a result of that, the effective nuclear charge on the electron is very, very less. So, what will happen? The effective nuclear charge is decreases due to the increase in size, and penetration effect is also less because the electron is added onto and subshell is having very low penetration effect. This will decreases the electron affinity. So we can say that penetration effect is proportional to electron affinity. Okay. When an electron is added onto a shell which is having very high penetration effect, the electron affinity is also very high. When an electron is added onto a shell which is having very low penetration effect, the electron affinity is very less. Okay. So we can conclude that the electron affinity, which is a periodic trend which will proportional to the nuclear charge and inversely proportional to the atomic radii, again which is proportional with the penetrating power or penetration effect of the sublevel electrons, and proportional inversely proportional with the screening effect of sublevels, as well as the electron repulsion. You should note this case for solving questions. Similarly, the electron affinity of noble gases and the elements having half-filled or fully filled electronic configuration possess zero electron affinity. They are having very, very less tendency to accept an electron. And the periodic trend of electron affinity. We have already discussed the periodic elements of periodic table, where the periodic trend, the electron affinity is more towards the halogen, the group number 17. So halogens possess very high electron affinity because of their very high tendency to accept an electron to complete its octet. Halogen possess very high electron affinity than oxygen family, which index greater than carbon family and nitrogen family, and metals in group 1 and 13, and finally group 2 metals. Okay.